Welcome to the 7th lecture on mass transfer operation. In this module, we are discussing on diffusion mass transfer. So, before going to the lecture, let us have small recap on our previous lecture. In our previous lecture, we have discussed measurement of gas phase diffusion coefficient, and under this experimental measurements of the diffusion coefficient, we have considered two methods. The first method is twin bulb method, and we have considered counter current diffusion for two components using the twin bulb method, and we have solved certain problems on this method. The second method we have considered is Stephan tube method, where we considered the diffusion of a component through non-diffusing B. In this lecture, we will consider three cases. One is gas phase diffusion coefficient predictions, then we will consider liquid phase diffusion coefficient measurements, and then third case we will consider the liquid phase diffusion coefficient prediction. The first one is gas phase diffusion coefficient prediction. Predictive equations. Basically, in many situations we have experimental diffusivity values for binary gas mixtures, and that are available in the literature. But still there are several mixtures for which experimental data are not reported. So, in this situation we can use suitable correlation to predict the value of diffusivity. These values, the predictive equations which are obtained from the predictive equation, is based on some relations which is developed for different system based on the variation of the temperature, pressure of the systems, or the molecular weight of the components or their molecular volumes. So, based on that, these equations, the predictive equations are proposed. One of the empirical relations is Fuller equations. So, a very simple and reasonably accurate empirical equations which was proposed by Fuller et al. In 1966 for the prediction of binary gas phase diffusivity, which is up to moderate pressure, which is DAB would be equal to 10 to the power minus 7 T to the power 1.75 divided by Pt total pressure, and then multiplied by summation over Va to the power 1/3 plus summation over Vb to the power 1/3 whole square into 1 by Ma plus 1 by Mb to the power half meter square per second. DAB is the diffusion coefficient of component A into component B mutual diffusivities, where T is the temperature in Kelvin, Ma and Mb are the molecular weights of component A and B, Pt is the total pressure in atmosphere, and Va, Vb are the atomic diffusion volumes, that is in meter cube. Now, let us take an example to calculate that diffusion coefficient. For mixtures of carbon monoxide and hydrogen, we need to predict the diffusivity using Fuller et al. 1966 formula for the following conditions. At 1 atmosphere pressure and 100 degree centigrade temperature. The second case is at 2 atmosphere pressure and 100 degree centigrade temperature, that means the temperature kept constant and pressure is doubled. In the third case is at 1 atmosphere pressure and at 200 degree centigrade temperature. In this case, compared to the first problem, the pressure remains constant and temperature is doubled. Now, let us solve this. So, Fuller equations we know DAB would be equal to 10 to the power minus 7 T to the power 1.5 into root over 1 by MA plus 1 by MB whole divided by PT whole into summation over VA to the power 1/3 plus VB to the power 1/3 whole square. Now, using values from the textbook, we can calculate, or the data would be given. Considered component A is carbon monoxide and component B is hydrogen. So, if we wanted to calculate summation over VA, which is carbon monoxide, would be equal to 1 into the volume of carbon plus 1 into the atomic volume of oxygen. So, it would be equal to 1 into 16.5 plus 1 into 5.48. So, it would be equal to 21.98. So, the molar volume is calculated for component A and its molecular weight Ma is equal to CO, component CO would be equal to 1 into 12 molecular weight of carbon plus 1 into molecular weight of oxygen 16, which is 28 kg per kmol. Similarly, for component B, we can calculate summation over Vb would be equal to 2H, which is hydrogen, would be equal to 2 into 2.31 would be equal to 4.62, and the molecular weight of hydrogen would be Mb would be equal to 2 into 1 is equal to 2 kg per kmol. Now, temperature is given for problem 1, temperature is 100 degree centigrade. So, we can just add 273 to get in terms of Kelvin. T would be equal to 100 plus 273 would be equal to 373 Kelvin. So, temperature is calculated and the unit of pressure in the formula is in atmosphere. So, PT it would be equal to 1 atmosphere absolute. So, if we substitute the values which we have calculated for temperature, molecular weight of component A and component B, total pressure and then the molecular volume of component A and component B in this Fuller equations, we can able to calculate the values for DAB. So, which would be equal to 1.159 into 10 to the power minus 4 meter square per second. So, this is the diffusivity of gaseous component. Now, for the second problem, when we change the pressure from 1 atmosphere to 2 atmosphere, keeping the temperature constant at 100 degree centigrade, we need not to calculate from the scratch. If we know the relations between the diffusivity and the pressure, we can have the data at 1 atmosphere pressure and 100 degree centigrade. Since their molecular volume and weights are same and at the same temperature, we can use the formula DAB is proportional to 1 by PT. So, if we use that formula, we can write DAB2 by DAB1 would be equal to PT1 by PT2. So, DAB1 is the diffusivity which is calculated at a particular temperature and pressure, that is at temperature T1 and then pressure P1, and then the DAB2 is at the same temperature and pressure at PT2. So, DAB2 would be equal to PT1 by PT2 into DAB1. So, if we substitute diffusivities using the first one, then we can get P2 is 2 atmosphere and DAB1 would be equal to 1.159 into 10 to the power minus 4 meter square per second. Now, if you substitute that, it would be half into 1.159 10 to the power minus 4 meter square per second, which would be 0.5795 into 10 to the power minus 4 meter square per second. Now, in case of the third problem, which is at 1 atmosphere pressure and 200 degree centigrade temperature. In this case, the pressure remain constant and but the temperature is doubled. So, in this case as well, we need to use the temperature correlations between the diffusivity and then we can calculate from the first one. So, that is why there is no need to calculate the other diffusivities from scratch, as they all have the same molecular volumes and weights, and that is at same pressure we can write DAB proportional to T to the power 1.75. So, we can write DAB2 by DAB1 would be equal to T2 by D1 to the power 1.75. Now, if we substitute the values T2 and T1 and then DAB1, we can get DAB2. So, which is T1 is 273 Kelvin and T2 is 200 is 473 Kelvin. Now, if we substitute DAB1, already we have calculated 1.159 into 10 to the power minus 4 meter square per second. We can calculate DAB2 would be equal to 1.761 into 10 to the power minus 4 meter square per second. Now, we will discuss the gas phase diffusion coefficient prediction. Chapman equation. In this equation, basically DAB is equal to 1.858 into 10 to the power minus 7 T to the power 1.5 divided by Pt sigma AB square zeta d into 1 by Ma plus 1 by Mb to the power half. In this case, T is the temperature in Kelvin, Ma and Mb are molecular weights of A and B, Pt is the total pressure in atmosphere, sigma AB is the characteristics length parameter of a binary mixture in angstrom, which is sigma A plus sigma B by 2, zeta d is collision integral is equal to function of k T divided by epsilon A B. So, this is we can write from here, it is epsilon A epsilon B to the power 0.5. Now, for mixture of ammonia and hydrogen, predict the diffusivity using the Chapman formula at 1 atmosphere pressure and 100 degree centigrade temperature. So, Ma is the molecular weight of ammonia, we can write is 17 and Mb is hydrogen. So, molecular weight is 2, temperature is 100 degree centigrade. So, which is equal to 373 Kelvin, pressure is 1 atmosphere total pressure. The Lennard-Jones parameters are given for ammonia, sigma A is equal to 2.9 angstrom and epsilon A by K would be equal to 558.3, sigma B is 2.827 angstrom and epsilon B by K would be equal to 59.7. So, now for ammonia hydrogen pair, we can calculate sigma AB would be equal to sigma A plus sigma B by 2 would be equal to 2.900 plus 2.827 divided by 2, which would be equal to 2.8635 angstrom. Now, epsilon A B by K would be equal to epsilon A by k into epsilon B by k to the power half. If we substitute the values, we will get it is 182.6. Kt by epsilon A, we can then calculate 373 divided by 182.6, which would be equal to 2.04. Now, collision integral would be equal to 1.075. So, if we substitute the parameters in this equation, Chapman equations, we can obtain the diffusion coefficient as 1.134 into 10 to the power minus 4 meter square per second. Now, we will discuss the another topic, liquid phase diffusion coefficient measurements. The first method which we will discuss is the diaphragm cell method. That is how we measure the diffusion coefficient in the liquid phase. A very dilute solution is taken in compartment 1. So, the top part of this is compartment 1 and a very dilute solutions are taken over here. A solution of slightly higher concentration in compartment 2. Molecular diffusion takes place through the narrow pores of the diaphragm cell. So, there is a diaphragm at the middle, from through which the molecular diffusion takes place of the components. Let the area of the diaphragm is A and the porosity is epsilon. The effective area for diffusion is A. The length of diffusion path is not equal to the thickness of the diaphragm, since the pores are not straight. So, basically if we take a diaphragm, the path of the diffusion or the pores inside the diaphragm are not a straight channel. It is a tortuous channel and the length, that is why we should not be equal to the thickness of the diaphragm. So, a tortuosity factor must be introduced in this. So, to calculate that, tau tortuosity factor would be equal to average or effective length of diffusive path divided by the diaphragm thickness. So, tau is the tortuosity. As the solute concentration is very low, bulk flow term can be taken as 0 and hence we can write Na would be equal to, that is the flux of component A would be equal to minus dAb dCA dH, which would be equal to dAb into the concentration gradient Ca1 minus Ca2 divided by H2 minus H1 into tau. We can write this would be equal to dAb Ca1 minus Ca2 divided by x d into tau, where H2 minus H1 is x d. So, let call this equation as equation A. We can write the flux equation for both sides of the diaphragm as follows. For cell 1, it is minus V1 dCA1 divided by dt would be equal to A into epsilon Na, this is equation B. Now, for compartment 2, we can write its volume is V2, which would be V2 into dCA2 dt would be equal to A epsilon Na, this is for this is we can call equation C. Now, if we add both equation A and B and C, and then if we substitute Na from the earlier equations, equation A, then we can obtain the following equations: dCA1 minus dCA2 divided by dt would be equal to A epsilon DAB Ca1 minus Ca2 divided by xd tau whole into 1 by Va1 plus 1 by Va2. This is equation D. Now, if Ca1 0 and Ca2 0 are the initial concentration, then we can write the boundary conditions for this. At T is equal to 0, Ca1 would be Ca naught and Ca2 would be Ca2 naught. At T is equal to Tf, Ca1 would be Ca1f and Ca2 would be Ca2f. So, these are the two boundary conditions we will obtain at time is equal to 0 and time is equal to Tf. So, using these two boundary condition, if we integrate equation D as we have derived before, we will obtain equation E like this. DAB would be equal to xd tau by A epsilon Tf whole into 1 by V1 plus 1 by V2 inverse into ln Ca1 naught minus Ca2 naught divided by Ca1f minus Ca2f. So, we can simplify this is equal to 1 by alpha Tf ln Ca1 naught minus Ca2 naught divided by Ca1f minus Ca2f. So, this is the final equations where alpha is equal to A epsilon divided by xd tau into 1 by V1 plus 1 by V2. So, alpha is the cell constant and can be determined by using a solute of known diffusion coefficient. Now, let us take an example. To measure the diffusivity of acetone in water at 20 degree centigrade, a diaphragm cell is used. Initially, compartment 1 of volume 50 centimeter cube is filled with 0.5 molar acetone in water and the compartment 2 of volume 55 centimeter cube is filled with water. The molar concentration of acetone dropped to 0.5 molar in compartment 1 after 40 hours. The cell constant is given as 0.3 per centimeter square. Now, we need to calculate the diffusivity of acetone. So, the data which are given V1 50 centimeter cube, V2 55 centimeter cube, then alpha cell constant is 0.3 per centimeter square, then time of operations is Tf which is 40 hours, we can calculate in terms of second. So, it is 144 not 1,44,000 seconds. At t is equal to 0, Ca1 naught is given is equal to 0.5 and Ca2 naught is equal to 0. At t is equal to Tf, Ca1f is equal to 0.4 and Ca2f we need to find out. The Ca2 naught equal to 0 at t is equal to 0 because the water in one side is pure water and it does not contain any acetone. So, Ca2 naught at t is equal to 0 is equal which is equal to 0. Now, if we do the material balance on acetone, we can write V1 Ca1 naught plus V2 Ca2 naught would be equal to V1 Ca1f plus V2 Ca2f. So, if we substitute the values from the data which are given, we can calculate CAF, Ca2f which is equal to 0.091. Now, all other values are known. If we substitute over here in this equation, DAB would be equal to 1 by alpha TF ln CA naught CA1 naught minus CA2 naught divided by CA1F minus CA2F. So, if we substitute those values, it would be equal to 1.11 into 10 to the power minus 9 meter square per second. Now, we will discuss the liquid phase diffusion coefficient prediction. There is a semi empirical relations which is proposed by Wilkie-Chang equations, and this is the diffusion coefficient is related with 1 point which is equal to 1.173 into 10 to the power minus 16 into phi into mb to the power 0.5 into t divided by mu b Va to the power 0.6. So, it depends on these properties of component A and B and the temperature. DAB is the diffusivity of solute A in solvent B, which is in meter square per second. Phi is the association factor. For water it is 2.2226 and for methanol it is 1.9, for ethanol it is 1.5 and for non associated solvent it is 1. Mb is the molecular weight of component B. T is the absolute temperature in Kelvin. Mu b is the solution viscosity which is in kg per meter second. Va is the solute molar volume at normal boiling point which is in meter cube per kmol. Va for is equal to 0.0756 meter cube per kmol for water as solvent. Now, let us take an example. Predict the diffusivity of acetone in water at 20 degree centigrade using Wilkie-Chang equation. The association factor for water is 2.26. The molar volume of acetone is 0.074 meter cube per kmol. The viscosity of water at 20 degree centigrade is 1.002 into 10 to the power minus 3 kg per meter second. The equations is known to us, the Wilkie-Chang equation. Now, the data which are given, if we substitute over here, we will obtain the diffusivity of acetone in water DAB would be equal to 1.04 into 10 to the power minus 9 meter square per second. Now, there is another equations is known as the Stokes-Einstein equation. A very large spherical molecule A diffuses in liquid solvent B of small molecules. In this case, the Stokes law was used to determine the drag on the moving solute molecules. So, we assume all molecules are alike and arranged in a cubic lattice. So, the diffusivity DAB is given as 9.96 into 10 to the power minus 16 T divided by mu Va to the power 1/3. In this case, DAB is the diffusivity of solute A in solvent B, Va is the solute molar volume at normal boiling point, T is the absolute temperature, M is the viscosity of solution. So, liquid viscosity varies linearly with absolute temperature. We can see DAB has a linear proportional which is proportional to T, directly proportional to T, and it is inversely proportional to the viscosity of the solution or of the medium. So, the well known Stokes equation shows this type of dependency as dAB mu by T is constant. So, if we just substitute, because the molecular volume of component is constant. So, if we multiplied dAB into mu divided by the temperature, which would be constant. So, this is all about the diffusion coefficient in the liquid phase prediction. There are many more liquid phase diffusion coefficient measurements equations which are not covered. So, please refer to the different text and reference books which are proposed to study, in particular Jean Copley's and B.K. Datta's book and also Treval's book for further studies. Thank you very much for hearing this lecture, and in the next lecture we will consider multi-phase diffusion coefficient.